I'm going to talk about something that's interested me for a long time, and that is the search for life in the universe. And I have on the, you see the picture, is the picture of the only known inhabited planet in the whole in the whole universe. So this beautiful planet that we live on with its seas and clouds and its atmosphere that life has changed to suit itself. But the point is, this is the only place in the universe that we know has life upon it. And so obviously this begs the question, are there other inhabited planets out there? But it's also, the more you think about it, it's a little bit strange that this is the only place that we know life exists upon. And the more we've explored the solar system, the stranger it gets, because we keep finding places in the solar system that we know either are or in the past would have been habitable places. So I don't have time to do a thorough survey of this, but if we just look at a few places in our own solar system, we start with Mars. So Mars has been a place where people have been interested in life for a long time, since H.G. Wells wrote War of the Worlds in 1899 or whenever it was. And we've been searching for life on Mars for a long time, and we still haven't found any. That in itself may say something. I mean, clearly, if there is life on Mars, it's not at all abundant, and it's hiding below the surface or something. It hasn't changed Mars into a blue-green planet in the way that life has changed the Earth into such a place. So there's food for thought there. On the other hand, as we've explored Mars with our rovers, so this is the Curiosity rover that's been crawling around Mars for 4 years now. It's an artist drawing, of course, but one of three actually robotic rovers which have been exploring the surface of Mars, and our spacecraft, which have been looking at Mars from orbit, have started turning up evidence that early Mars, at least Mars in the first quarter of its history, Mars in the first 1,000 million years of solar system history, was a much more habitable place than it is now. And I'll illustrate this with just the one picture. The picture at the upper left here, with the greens and blues on it. This is a photograph from an orbiting spacecraft. It shows it shows part of the rim of a large 50-kilometer diameter impact crater. So this is the rim of the impact crater. But it shows multiple evidences that liquid water flowed on Mars in the past. In fact, in this one picture, there are 3 pieces of independent evidence that early Mars had liquid water on its surface. The most obvious is this river valley, dried up river valley now that's meandered around here, burst through the rim of Jezero crater. So this is evidence for liquid water, or at least liquid something, but come to the fact we know it's water shortly. Then there's, in the crater floor, there's this structure. Now this is a delta. It's a dried up delta, and it's one of hundreds now that have started to turn up on Mars. Rivers produce deltas when rivers carrying sediment flow into standing bodies of water, and then the river carrying the sediment slows down and the sediment drops. Delta is formed. So this implies that not only was the water in this river, the whole of Jezero crater, which is 50 kilometers across when this was all going on, was once full of water. It was once a crater lake, and it's a very large one, and it's one of hundreds that have now been found on Mars. So there was a lot of liquid water on early Mars. But then the clinching argument of these colors, these are false colors, but they're assigned to the spectral properties of the surface rocks. And the blues here correspond to minerals igneous minerals that basaltic lavas are made out of, and you expect for the crust of Mars. But the greens and turquoisey colors, these indicate the presence of clay minerals. And clay minerals are what you get when you erode volcanic rocks with liquid water. And so the fact that clay minerals are cropping out in this delta implies that it was water. It wasn't liquid lava, it wasn't liquid carbon dioxide, it wasn't liquid anything else, because in order to make clay minerals, you require liquid water. So all of this was going on about 3,500 million years ago, in the earliest part of Mars's history. You would have a planet full with rivers and crater lakes, must have had a thicker atmosphere, must have had a higher temperature for water to be stable. By any stretch of the imagination, would have been a habitable environment, for microorganisms at least. What we do not know is whether it was ever inhabited. And that's what's driving a lot of Mars research. But if it was, then life that got going in that environment either became extinct or it's migrated underground. It hasn't flourished and taken over the whole planet in the way that it did on the Earth. And of course, it may not have evolved there at all. Just because the environment was habitable doesn't mean that it was inhabited, because there may be things in the origin of life which make originating life from non-life very much harder than merely having a habitable environment with liquid water. So I'll return to that. Then there are places in the outer solar system. This shows the southern hemisphere of Saturn's moon Enceladus, which is actually seen venting water into space. These are plumes of water emanating from the south pole of Enceladus. Enceladus is a small moon, 500-kilometer diameter moon with an icy crust. But underneath the icy crust, there is an ocean of liquid water because we can see the water venting into space. And it's now becoming clear that many of the icy moons in the outer solar system, Ganymede, Callisto, Titan, Enceladus, beneath their icy crusts have oceans of liquid water. These may also be habitable environments, but of course searching them to see whether there's anything alive within these oceans will be a much, very, very significant challenge. But the point is that in our own solar system, we see all of these habitable places. And then, the most exciting thing that's happened in astronomy in the last 20 years is the realization that solar systems like our own are not at all rare. The first planets found orbiting solar-type star occurred in 1995. And in the last 20 years, we've now found 4,000 planets orbiting other stars. And there's a sufficient statistical base now for us to be confident that almost all stars will have planets. Already we can say that 70% of stars have planets. But we also know our statistics are not complete. And that 70% can only go up. So by the time the statistics are all in, it's going to turn out that 90% or more of stars are accompanied by planetary systems. You may recognize this photograph. It's part of the southern Milky Way. A sort of beautiful bright stars. This is the Southern Cross. This is the nearest star, Alpha Centauri, 4 light years away. This is the Southern Coal Sack, which is a foreground dust cloud, the kind of cloud that collapses under gravity to make new stars and planets. And then in the background, you've got millions and millions of stars. Well, the thing is, we now know that all of these stars will have planetary systems. And then we look at our own solar system and we see the range, diversity of planets, and that many of them either are habitable or have been inhabited. There's no getting away from it, there have to be an enormous number, millions and billions of habitable planets in the galaxy. The question is that enough? But I think, just because they're habitable doesn't mean they're inhabited, right? So all we can say is that if life is not common in the universe, it's not because there's a shortage of planets. There'll be millions and billions of planets. So, we've been searching our own solar system for evidence of life, either in present, in the current extant life in the solar system, or life in the past. We haven't found evidence for either yet, but it's important that we keep looking. And eventually, once we've explored Mars and the icy moons sufficiently, we will have an answer to this question. It may take many decades. But it's already clear that if life arose elsewhere in our solar system, not only has it not flourished anywhere else apart from the Earth, it's never can have, certainly at the present time, even if it exists, it can only be at a microbial stage of existence, because otherwise we would know. And even that isn't certain. So the only other thing that we can do, until we can build starships to actually go to the stars and explore planets around Alpha Centauri with rovers like the Curiosity rover, that's obviously a long way in the future. The only other thing we can do is look at the stars with telescopes from the Earth. We can start studying these planets that we found and look to see whether their atmospheric compositions indicate atmospheres that have been changed by biology. So astrobiologists call these molecules biomarkers, things in planetary atmospheres that would indicate life exists on the planet. To do that on these newly found planets is a tremendous observational challenge. It is something that will develop over the coming 20 years. It requires large telescopes, ideally large telescopes in space, like the James Webb Space Telescope, which is to be launched soon, we hope, and other large space-based telescopes. And so we will start to get statistics eventually, but it will take several decades given the size of the instruments that we need. We'll be able to start analysing planets orbiting nearby stars, studying their biosignatures, looking for biosignatures in their atmospheres, and we'll get some sort of statistical answer as to whether biosignatures are common in extrasolar planets or not. The other thing we can do at the other end of the observational spectrum is we can say that if life had arisen on any of these other planetary systems and evolution had gone through a kind of sequence of stages analogous to what it did do here, some fraction of these planets with life may have given rise to intelligent beings capable of producing technologies. And we might be able to observe the technologies. And in particular, we might be able to observe artificial radio transmissions or artificial laser beams or artificial signals of some kind. This is called the Search for Extraterrestrial Intelligence, SETI. It is usually performed in the radio spectrum. This is the Parkes Radio Telescope in New South Wales, scanning the heavens for signs of artificial radio signals. This has been going on for 50 years now, or actually longer. So it started in 1960, the first ever SETI search. And it hasn't found anything either. Over 50 years, the galaxy seems very quiet. Now, again, it's too early to draw too much from this conclusion. One could argue lots of reasons why aliens might be present. They might not be transmitting radio waves. They might be deliberately not doing so. They might be transmitting at frequencies that we're not listening into. Maybe we're looking at radios and they're using lasers or something. Although we've now started to look for artificial laser signals and haven't found any of those. So it's too soon to draw a conclusion, but the fact is we've been looking for 50 years. If this carries on, and the techniques for SETI are getting more and more sophisticated, more and more sensitive, this carries on for another 50 years and we haven't found any signals, then we're going to maybe start to think that intelligent life that transmits radio waves and builds radio telescopes might be rare. Which would be consistent with life itself being rare, of course, but in between those two, there are a wide range of other possibilities. So this shows Frank Drake. Frank Drake, who conducted the first SETI search in 1960, he called it Project Ozma. He looked at the two nearest single solar-type stars for a few hours with a radio telescope and detected nothing. And since then, the searches have got bigger and bigger and more sophisticated, and they've still detected nothing. But Drake tried, in 1961, he tried to quantify this. He tried to think, how many, suppose life exists elsewhere in the universe, how many technological civilizations do I expect to find? This would give astronomers a clue as to how many stars they should be looking at. How much of this very expensive telescope time should be devoted to SETI rather than to mapping hydrogen clouds in the galaxy or other more prosaic astrophysical tasks. So Drake came up with his famous equation, which he first codified in 1961. In which he reasoned that the number of technological civilizations extant in the galaxy at any time, that's the big N at the front of the equation, would equal all these things multiplied together. So and I'll explain why I did it this way in a minute, but let me just define the terms. R subscript star is the rate of star formation in the galaxy, which astronomers do know. It's of the order of 1 per year, except in recent years it's been creeping up. It might be several per year, actually. It might be 7 per year. But anyway, a few per year. When Drake wrote his equation, it was about 1 per year, so 1 or a bit more. Then F subscript P is the fraction of stars, those stars which form planetary systems. Now, in 1961, no one had any idea what that was. But now we do. Thanks to the last 20 years of astrophysics research, we know that fraction is about 1. I mean, I told you it's at least 0.7. It's probably going to be 0.9 or more when all the statistics come in. So in round numbers, all stars have planets, which means the fraction would be 1. The fraction of stars with planets would be 1. That would be F subscript P. Then he realized that stars typically don't just form one planet. I mean, our solar system's got... So when I was at school, it was 9 planets, but now it's only 8 planets, as you know, because Pluto's been demoted, but nevertheless Pluto is still there as an astronomical object. So obviously, and we've got all these moons, right? The moons of Jupiter and Saturn, like Enceladus. So n subscript e is the number of planets within each solar system that have habitable environments. So for the solar system, that is at least 1, because the Earth is habitable. But you could justify a number like 3 or 4 for that. Early Mars was habitable, Enceladus is habitable. So anyway, a few. And the thing is, we've got this part of the Drake's equation, we've got reasonably good estimates for what these numbers might be. But then the latter half of the equation, there are things that we know nothing about and that we desperately need to find out, and which is driving most of astrobiology research today. F subscript L is the fraction of planets with habitable environments on which life actually evolves or originates. We don't know what that is. It could be very common. It might be that on nearly all habitable environments, life originates. But if that were true, life should have originated in Jezero crater when the crater was full of water and everything. If that were true, when we explore Mars, we'll find evidence for at least past life. So there's a way of constraining this number by exploring our solar system. Obviously, if this fraction is a lot less than 1, then we might find habitable environments in the solar system like early Mars or Enceladus, but they won't be inhabited because the fraction, it's difficult to evolve life from non-life. Anyway, we don't know what that is. It's important for us to find out. F subscript I is then the fraction of such life that becomes intelligent eventually over evolutionary timescales. We don't know that either. F subscript C is the fraction of such intelligent life that can communicate across interstellar space. Now here, Drake's really sort of showing his sort of bias, inherent bias, because he's written n here. Strictly n is not the number of intelligent civilizations in the galaxy. That's what you'd get if you stopped here. It's the number that can communicate across interstellar space, because he really wanted an equation to inform the SETI searches. And to a radio astronomer, you're communicative if you can build radio telescopes, essentially. And then if you take this, the rate of star formation multiplied by all these fractions is the rate of formation of communicative interstellar civilizations per year. If you've taken the star formation to be per year, multiplied it by all these fractions, this is the rate of the formation of communicative technological civilizations in the galaxy per year. And then if you want to know how many there are at any given time, take that formation rate and multiply it by the lifetime of these civilizations, and that's the L at the end. And we don't know what that is either. So in a sense, the Drake equation sums up a lot of ignorance. It's not very predictive because you can put in what you want and to some extent get out what you want. On the other hand, it has been a very useful tool because it does break down the problem into easily manageable chunks. I mean, space exploration and astronomy have already started giving us answers to these, which we didn't have, 50 years ago. Future exploration may start to put some constraints on these fractions, and that's kind of what we want in order to get a realistic estimate. Anyway, there are two. Obviously, you can get what you want from the Drake equation. You can go home and put in your own numbers, but there are clearly two extreme possibilities. Drake is an optimist. Drake is still alive, and he's still an optimist. And Drake, despite having not discovered anything for 50 years, he's still an optimist. And he's got some reason to be, in a way. But an optimist says that we already know there's one star, but bear in mind it might be a bit bigger now. That makes it even more optimistic. But then an optimist would set all these fractions to 1. All stars have planets. We now know that's true. A real optimist might make this number a bit bigger than 1, but anyway, let's have it at 1. And then you can't get any optimistic than having these fractions bigger than 1. So an optimist would say, given the habitable planet, life inevitably evolves. Natural selection inevitably will lead to intelligence, that's F subscript I. Intelligence will inevitably discover how to communicate across interstellar space, that's F subscript C. Put those equal to 1. 1, 1, 1, 1, 1. And then your estimate for the number of civilizations, communicative civilizations strictly in the galaxy today, be 1 times 1 times 1 times 1 times 1 times L. If you've measured the star formation rate in stars per year, you have to measure the lifetime in years. So if you thought a technological civilization would only last for 100 years, you're expecting 100 in the galaxy at the present time. And so they'd be pretty thin on the ground, given that the galaxy is 100,000 light years across and contains 100,000 million stars. If you thought, Carl Sagan used to argue this was a million, like civilizations might last for 1 million years or longer once they discover their technology. So that's an optimistic view of technology. Technology can go either way. It can either make you immortal or it can kill you after 10 years if you start dropping nuclear bombs on each other, right? So the whole spectrum, right? And this is in the realm of extraterrestrial sociology, extraterrestrial politics. We know nothing about that. A figure the SETI optimists like Drake is 1,000 years. And the reason they like 1,000 years is it seems not unreasonable that a technological civilization might last for 1,000 years. That's comparable to civilizational durations that we're familiar with in our own very limited history, although that is a very anthropomorphic view. There's another reason why they like 1,000 years, though. If L was 1,000 years, it means there's 1,000 it implies there'd be 1,000 technological civilizations in the galaxy today. That means there'll actually be about 1,000 light years away, apart from each other on average. And the SETI people kind of like this because they know they haven't detected anything yet in 50 years, but they also know their distance limit to which these searches are sensitive is a few hundred to 1,000 light years. If there were civilizations 1,000 light years away from us and it was transmitting to us, it wouldn't be surprising that we hadn't detected it yet. On the other hand, that we might wake up tomorrow morning and detect it. So this can keep the SETI people going, right? This is a reason for their optimism. It's not an extreme number, like 1 million civilizations in the galaxy that Sagan and others like to argue. But it's not a very pessimistic one. And it means that a signal might be detected within our lifetimes if there were of the order of 1,000 technological civilizations in the galaxy at the present time. So you can't get more optimistic. You can't get more optimistic than that because we've set all these fractions to 1. But you don't have to be optimistic. There are reasons, I think, if you look at the evolutionary history of life on Earth, not to be optimistic. And the fact that we haven't found any life on Mars, despite the fact we know Mars was once habitable. So if we just look, this little diagram shows my potted history of life on Earth. The planet is 4,500 million years old, so these are timescales in thousands of millions of years. Planet formed here. We're at the top. Things have happened in this huge length of time that have resulted in us being here in this room in 2017. Obviously, in order for that to happen, life had to evolve on this planet. Well, there is evidence that it did so. Our earliest fossil evidence for life on Earth is sort of back here, 3.5, 3.8 billion years ago. This is some reasons to be optimistic for life on Earth, because it implies that although we don't know how life originates from non-life, it did happen on this planet very early after the planet formed. That might imply that we don't know how life originates from non-life, but nature knows how to do it, and nature knows how to do it quickly on planets that were like what the Earth was, which is a very different place, but planets that were like the Earth was back here. Planets with liquid water on their surfaces, a lot of volcanic rock, and probably thick carbon dioxide atmospheres. On such a planet, life did arise on the Earth, and it did so relatively quickly. So you might base on that our view that life gets forming on planets quickly, once on habitable planets quickly, therefore life will be common. Of course, we're talking about microbial life only, and we're talking about an example of one that strictly you cannot generalize into the whole universe. But if looking at our example of one, that's a message you could take from it. But then, look at this. We've got 3,000 million years. I'll have to skip all this. I mean, a lot of very interesting biology was happening in this time scale. But just draw your attention to the first fossil evidence we have for multicelled animals, which are basically animals at a sort of jellyfish level of multicellular complexity. They appear in the fossil record here, 0.6 billion years ago. So for the vast length of the history of this planet, the planet's been inhabited, but it's been inhabited only by microorganisms. So that could imply 3,000 million years is a long time. I mean, not only is it 3/4 of the age of the Earth, it's a significant fraction of the age of the universe, that it's taken life on this planet to evolve from a unicellular level of complexity, which is still very complicated, actually, to a multicellular grade of complexity that then natural selection can work on to produce many multifarious animals and plants and eventually ourselves or intelligent creatures at the top. But it took a long time. So if you were to extrapolate this out into the wider universe, you might argue that microbial life may be common in the universe. It gets going quickly on suitable planets, but then evolving multicellular life and animal life and anything that can develop a technology, this is probably really hard because it took a very long time, and therefore technological life might not be common in the universe because it's so many steps have to be gone through to evolve it. Now, just as a quick aside, if this story I've told you is on the right lines, it makes some predictions. If it's true that life always gets going early on planets like what the Earth was 3.5 to 4,000 million years ago, then that's a prediction that life should have started on Mars, because 4.5, when Jezero Crater was full of water 3.5 billion years ago, it was very similar to what the early Earth was like at the same time. Planets have diverged a lot since, but at that time they were similar. So if we go to Mars and we find there was life, we find fossil microbes in that delta in Jezero Crater, yeah, it would support this view that life is quick to get going on warm, wet, rocky planets. And there are billions of those in the galaxy. We already know that. If, on the other hand, we get to Jezero Crater and we find that despite being a perfectly habitable environment, life never started, we'd have to start thinking, maybe there's something in the biology that means life doesn't automatically get going just because you've got a nice, warm, wet, habitable environment. And life would not be common, arguably, in the universe in that case. The point is we can explore that, we can test that hypothesis by exploring our own solar system. Whether intelligent life eventually evolves, we have to go to the stars, because it's obviously not happened elsewhere in our own solar system. So we have to start, and this would be where the SETI comes in, because then if you start detecting even one other extraterrestrial radio signal from another solar system, then that tells you that other technologies have arisen elsewhere in the galaxy, and it may be rare, and it may take a long time, but it would be experimental evidence that intelligence exists. But anyway, the thing is, I said we don't have to be optimistic. And one of the earliest people to intuitively see this was Alfred Russel Wallace. Can I just ask, who has heard of Alfred Russel Wallace? Oh, good, because Alfred Russel Wallace deserves to be much better known than he often is. So Wallace, as many of you will know, was the co-discoverer of the principle of natural selection with Charles Darwin. And it was Wallace's letter that was then what is now Indonesia to Darwin in about 1858 that suddenly Darwin realized other people were thinking along these lines, and he had to get The Origin of Species out pretty quickly before other people sort of scooped his idea. Anyway, Wallace was a very interesting person, and he had an interest in life in the universe. He wrote what could be arguably the world's first astrobiology book in 1904, and it was called Man's Place in the Universe. But it's interesting because here is a man who was at the very birth of evolutionary biology, and he was trying to apply some of the principles of evolutionary biology to the question of will there be other civilizations out in the universe. Now, here's a quote from his book. Now, it's written quite slightly long-winded Victorian prose, but it's still worth reading it. What he says is, given the evidence as to the number of very complex and improbable conditions which are absolutely essential for the development of the higher forms of life, he's here looking at it through the lens of someone who understands natural selection. You can have simple life, in inverted commas, because no life is simple. But then, in order to evolve that into a creature which can build a civilization and a technology, so many steps, right? If you just look at our own evolutionary history, not all of which look like they would need at all have been inevitable. Many of them were contingent on chance events, like meteorite impacts extincting dinosaurs and things. Anyway, many chance events, hurdles that the biology has to go through before it produced us. So he realized there was this whole sequence of events, evolutionary events that life had to go through, each one of which may have had a low probability, and then you multiply these low probabilities by each other. and you end up with something that could be very improbable by the end. So he has a stab. He says, we've got all these improbable conditions that need to be met. So he has a go. The total chances, so it seems to him that the total chances against the evolution of man, or an equivalent moral and intellectual being, these would be the intelligent aliens, will be represented by 100 million of millions to 1. Right, now he's just guessed this, 100 millions to millions to 1. He thinks it's very unlikely. Intuitively, he's got maybe one chance in 100 million that will evolve something like human beings. Anyway, the thing is, that is a probability. If you were to just take this guess, because clearly all it is at first sight, a probability of 100 million to millions to 1 is a probability of 10 to the power of minus 14 for F subscript I in the Drake equation. So you can put that in. We can be optimistic about all the other numbers, and again, you don't have to be. Well, you do have to be for these, because we now have astrophysical constraints on these. But it doesn't follow. For example, we don't know the F subscript L is 1. We don't know that that's what we need to test on Mars. That might be a very low number as well. But let's just assume you can evolve simple life out of non-life with a high probability, arguing that it happened quickly here. But that would be your sole justification. The more we explore Mars, we will be able to constrain that. But then take Wallace's number for the probability of evolving intelligence from life as 10 to the minus 14. And then if everything else is 1, the number of technological civilizations you expect in the galaxy at any given time would be 10 to the power of minus 14 times L. Suppose you take the lifetime of each civilization still to be 1,000 years. That would be 10 to the power of minus 11 times L. So what does it mean to say there are 10 to the power of minus 11 civilizations in the galaxy at the present time? Well, all it would mean is statistically you'd have to search 10 to the power of 11 galaxies and you'd find 1. There are about 10 to the power of 11, 100,000 million galaxies in the observable universe. So if Wallace's intuition for the difficulty of evolving intelligent life from life was in the right ballpark, we would be it. Not only in the galaxy, but in the entire observable universe. Between these two extremes, of course, there are other possibilities, and it's putting constraints on these other numbers. That's what these other probabilities, that is what's driving a lot of astrobiology research. So this is my last slide. Here is a quote from another great Victorian scientist, William Whewell, who also wrote a book in about in the 1850s, what does it say, 1853, searching for life elsewhere in the universe. And he has this statement in it where he says that the discussion, and I notice this is before natural selection. It's before Darwin and Wallace had their key insight. Anyway, Darwin had his insight, but he'd kept it to himself. Anyway, so Whewell writes that the discussions in which we are engaged, looking for life elsewhere in the universe, are at the very boundary regions of science, at the frontier where knowledge ends and ignorance begins. And the thing is, 150 years later, we're still there at that boundary. Despite all the advances in astronomy and biology and geology and planetary science over the last 100 years, we still do not have an answer to this question. Planet Earth is still the only known inhabited planet in the universe. And we really do not know whether we should be expecting to find others or not. We're still at this border between knowledge and ignorance. So the only way to become less ignorant is to get out there into the universe and explore it. And eventually, we explore it deeply enough, we will find the answers. So there are several things that we can do. We should be continuing our exploration of Mars for the reasons I've outlined. The early history of Mars contains a lot of answers, even a negative answer, that life never evolved on early Mars, despite it being habitable, would constrain our fraction for F subscript L in the Drake equation. We should continue to... And the discovery of life on Mars would give as an answer. It would tell us F subscript L is about 1. The fact that life's evolved independently on 2 adjacent planets within, at the same time. We should continue searching other stars and searching for planets orbiting other stars and making astronomical measurements of the spectral measurements of the compositions of exoplanet atmospheres to look for biomarkers. Within the next 20 or 30 years, we'll start, I think, to be able to at least begin to be able to address this question statistically. If we find 100 planets orbiting other stars in the so-called habitable zone where they ought to be warm and wet and habitable. And half of them have strange atmospheres with oxygen and methane coexisting and things that look out of chemical equilibrium. This wouldn't be a proof, but it'd be strong evidence that they have life on their surfaces, something strange going on. If, on the other hand, we look at these 100 nearest planets and we find that, yeah, they're all like Venus and Mars, they all have just carbon dioxide atmospheres in chemical equilibrium, no evidence for anything going on at all, and we've searched 100 of them, we'll start to think, yeah, maybe life isn't quick to get going on planets that are, even if they are warm and wet and habitable. Anyway, we'll start to get answers to that question, I think, statistically within the coming several decades. And of course, we pressed the wrong button. We should continue with the SETI searches because Drake and Sagan et al., they may be right. We may switch on the news tomorrow morning and a discovery may have been made. The point is, unless we continue to look, we'll never know. So I think really the argument is one of we continue to search the universe and eventually we will transition across this boundary from ignorance into knowledge. I'll end there. Thanks very much.